Ismail to just say a few words about Naeem, introduction of Naeem, and then we'll pass on to Naeem. So Ismail, please.
Yeah, good evening, everybody. Bismillahirrahmanirrahim. Thank you. I think this is one of the largest audiences we've had. And I'm really very, very honored indeed to welcome Naeem Hussain to make the presentation for us. I have our paths crossed in 2015, no, sorry, 2016 also. And I think Naeem's reputation precedes him. The very preeminent eminent civil engineer, as now been mentioned, the global bridge design leader of Arup, where he's also a director. He's had a lot of major bridge projects in the world, including the Stonecutters Bridge, the Queensferry Crossing in Scotland. Awards-wise, Prince Philip Medal by the Royal Academy of Engineering. He was inducted into the Scottish Hall of Fame, and he was named a Fellow of the Royal Academy of Engineering in 2020. I think it is really a very big honor to have somebody of such a global stature making a presentation to us. And without much ado, I would like to welcome Naeem, and please share your thoughts and your knowledge with us, your experience with us. Welcome, Naeem. Thank you.
Can you hear me now?
Yes, we can.
Okay, so Assalamu alaikum, and hello to everyone, and a special hello to Baria, who's, I believe, is joining all the way from the Arup office in the UK. So Baria, it's good to see that you made an effort to join. I hope you will enjoy the presentation. So since it's late, maybe I just go straight away into it. So what I'm going to do is to describe a review of sea crossing bridges. Okay, it's very slow, the computer. Let's see. Right. So as a background and as an introduction, can I, whoever is controlling this, can we remove the faces so that I can look at the screen? If you can put it down.
Yeah.
Can I, or do I have to do it?
Yeah. I can stop your video if you want, so that.
Yes. Might be better to stop everybody. Yeah, that's better.
Yeah. All right.
Okay. Thanks a lot. So the introduction, basically infrastructure, plays a key and vital role in the economic development and well-being of a region or a country. And waterways, whether they are wide rivers, bays, or estuaries, mean large detours by land or use of ferries, which can severely hinder the movement of people and goods, and this limits the economic development. So in the last, like since the 1990s, or even earlier than that, since the 1980s, this has led to the bridging of these waterways with road and rail bridges. And especially since the 1990s, several large sea crossing bridges have been built. The interesting thing is that the method of construction has varied for these crossings, but the emphasis has been on fast construction with prefabricated elements. Another feature of the crossings has been bridging of navigation channels associated with long waterway crossings, leading to development of long-span cable-supported bridges, which can be suspension bridges or cable-stay bridges. So what are the features of sea crossing bridges? It depends upon its location. The primary feature of fast track sea crossing bridge construction is that foundation and substructure construction should proceed in parallel with superstructure elements being precast or prefabricated off-site in factory conditions, which can lead to quality construction and shortening of the construction period. This is quite important. Another thing is that design for ship impact is also an important feature for navigation channel bridges, and various protection methods have been devised to safeguard the bridge towers adjacent to the navigation channel bridges. I'll just give one or two examples of that. So for this talk, by way of example and the features and development of the following crossings, I'll describe, in which I have been personally involved. So the number of crossings I've been involved with, which is the Öresund crossing between Denmark and Sweden, the Shenzhen crossing between Hong Kong and China, Incheon Bridge, Korea, Hong Kong, Zhuhai, Macau Bridge, China, Queensferry Bridge, Scotland, Brunei, Tamrong Bridge, and the Batan Cavite, which I was talking to Ismail a few minutes ago. I'll start with the Öresund crossing. And on this picture, you can see the map of Northern Europe. And you've got Sweden here. I don't know if you can see my cursor. And you see this red line where is the Öresund link, which connects Sweden, the south of Sweden, with Denmark. So at the time in March 1991, there was a treaty reference scheme, which was this alignment that you see, more or less like a straight line. And then in that hash bed, there was artificial island, and then connecting to Copenhagen. There was an international design competition that Arup took part in. And what we did was that instead of a single level bridge, we made a double-decker bridge, because this was both a railway and a road bridge, and I'll explain why we did that. But instead of having a straight alignment, we made a curved alignment. And the reason for that was that in the original reference scheme, there were two navigation channel bridges of shorter span, like 250. But we combined them into one larger span of roughly about 490 meters. And one of the criteria was to have the minimum blockage. Now, I'll speak about that in a moment, for the water to flow into the Baltic Sea. So in order to reduce the blocking, we made two smaller islands. And to add a visual link, we have one span, as I said. And then we separated the road and rail traffic for better views, safety, and also operational flexibility. And from an architectural and aesthetic point of view, we put an S-curve in the alignment. Now, what happens is if you have a very long bridge and it's very straight, all you see is the tarmac in front of you, and you can't really see the bridge or the landscape. But if you put an S-curve, you get different views of the bridge. Eventually, because of certain constraints, we couldn't do an S-curve, and we ended up with a C-curve. And you can see the elements of the crossing over here. So there was a 4-kilometer immersed tunnel. The reason for that was that if you put a big bridge here, it would have towers, and then that would be within the airport height restrictions of the airport. So you have an immersed tunnel, an artificial island to bring the railway and the road up, and then an 8-kilometer bridge to connect to Malmö. And that shows the final outcome. And you can see the 140-meter approach spans double-decker. The reason for making this bigger, as I said, was to have the least obstruction for water flow into the Baltic. On an average statistic basis, if water enters the Baltic, it takes something like 70 years for the water to get out of the Baltic. And what that means is the Baltic is a very salty sea and is very ecologically sensitive. And so to flush the Baltic Sea, you needed to have about 0.5% obstruction to the water flow. So the longer the span we could make and the narrower the piers we could make, there would be the least obstruction to the water flow. So the main span was 490 meters. And you can see over here the foundations are quite shallow because at the mouth of the Baltic, it's like a ridge. And that is what creates the Baltic and doesn't allow a lot of flushing of the water. So on this diagram, if someone can tell me they can see my cursor or not, and someone just...
We can.
We can, good, okay. So you can see on the approaches, we have like diagonals of 45 degrees, but we did a harp arrangement of the stake cable floor. And then the angle of the truss is in line with the cable stage for visual reasons and make it look as the connection between the harp and the deck itself. This is the cross section. You can see it's double-decker bridge with 2 lanes of traffic on top and a high-speed railway underneath. And for the cable stay portion, we keep this basic similar cross-section, but we have these brackets that come out where we have the stay cables for the bridge. You can see from here what I was saying about trying to build offshore in fabricated conditions. And this is in the Malmo dry dock. And these are the foundations for the towers. So these were built, and you can see the size of this foundation compared to these 2 people down in this photograph. It gives you something like 40 meter by 40 meters square cellular foundation. And then these were floated out from the dry dock, taken to the site, and then positioned by GPS-controlled barges, and then dropped into the sea. And it's about something like 10 meters of water. This shows the fabrication of the column. Now, some of these columns were up to 50 meters high. And whilst we are doing the foundation works, we are also casting the columns and also prefabricating the decks. And the whole bridge design, we actually based it on the availability of this floating erection vehicle. It's known as the Swan. And this was, first of all, commissioned for the suspension bridge called the Storbælt in Denmark. And then this vessel went all the way to Canada to do another bridge. And then we got it back here to do this bridge. And this floating crane, it can lift up to 6,000 tons and with a 1,200 ton lifting tackle. So it can lift something like 7,200 tons. And here you can see on the bottom right-hand side, so his hull is like a catamaran, 2 different hulls, and it can float and come around the pile cap and then drop the column. And the crane was also used to lift this 140 meter span double-decker deck, which is a composite deck, and then put it into position. And we show on the 14th of August, 1999, erecting the last span between the cable stay bridge and the approach viaducts. This is the completed bridge, and it's become, as usual, like most bridges, it attracts a lot of people and it becomes a tourist attraction. And you see a lot of people come to see it. So I jumped from Europe to Hong Kong, and I actually, after I came to Hong Kong in 1998, while the horizon was still being built. And you can see on this red line is the deep bay. We built a bridge between the west side of Hong Kong and the Shenzhen on the China side. This bridge is across the water is approximately 5 kilometers across the water. This is the boundary between the mainland and Hong Kong. Now, the interesting thing is because it was across 2 jurisdictions, the design code had to satisfy both the British standard codes that we use in Hong Kong and then also the mainland China design codes. So we had to check each other's work. But the interesting thing is that no matter which code you use, the final result actually did not make such a big difference. There was not the bridge sizes came out to be almost the same, which again shows to prove that if you have design codes, at the end of the day, they're taking the same kind of traffic, and most codes are written and you get roughly the same kind of answer. So this is a graphic of the bridge. And you can see on this side on the graphic, and below there were one bridge was built on the China side, the cable stay bridge, another one on the Hong Kong side. Now, originally we had towers leaning away from each other, like a dynamic thing. But when we showed this to the joint committee, they went very quiet. They said, this is very aggressive. They are facing each other. They said, no, we are brothers. We want you to make the towers lean towards each other. And I said, well, surely, okay, why not? So from brotherly love, we put the towers leaning towards each other. And you can see from here that there are, as I said, 2 cable stay bridges. The marine viaducts, again, very similar issues like many crossing. Again, deep bay is very ecologically sensitive. So we deliberately buried the pile caps so that we will not obstruct the water flow. And we made the spans as reasonably long as we could to make them an economic design. So there were 75-meter spans, end span was 70 meters, to get about 3.8 meters. And that shows the general arrangement of the cable stay bridge. In effect, one tower means that it was equivalent to a 420-meter bridge if we had 2 towers. So what did we do in terms of construction? Same theme as I was explaining before. While we were doing the foundations, the pre-cast segments were being cast. So that as soon as the foundations were ready, we could start erecting the decks. And these were done as balanced cantilevers with a launching gantry. That means from a pier, you balance the structure out on either side of the pier. And because there were 3 lanes and a hard shoulder in each direction, we had 2 separate boxes. And then you can see from here, they were built side by side. And the launching gantry did on one side first, moved across, and then to the other side. Towards the Hong Kong side, very shallow water, a lot of oyster beds. So there was an effect of the oyster farmers. So a trestle bridge was built out over this mud flat, and then work was done from the trestle bridge. But out in the more deeper water, it was built from it was difficult to transport from the land. So the bridge was actually built from the sea back towards the land, because it would mean that we could deliver the segments in the deep water and then move them along the already constructed deck, the construction front. So upriver from Hong Kong or the Pearl River estuary, there are lots of precast factory that can cast the segments. So the segments were all done in China and then brought into the Hong Kong waters. This shows the completed deck, 2 separate decks. Each of those decks is roughly about 16 meters wide to carry 3 lanes and a hard shoulder. So again, typical marine construction. And these are some completed photos of the bridge. You can see on the right-hand side, the curve and the 2 navigation channel bridges. And now I'll tell you something a little bit about the Incheon Bridge in Korea. On that one, we were the independent checker, not the main designer. And this was an 800-meter span. And the time of when this was built, this was going to be I think the 5th longest cable stay span in the world at that time. Quite deep water, something like 30 meters of water. And you can see over here, I was talking about ship impact. These towers were safeguarded by these circular caissons, which are up to about 30 meters deep, 30 meters in diameter, so that if a ship hit, they were coming towards the tower, would actually hit these caissons. Main viaducts on this one was used full span launching. What that means is that a whole span of 50 meters, the 3 lanes and a hard shoulder, was cast off-site and then lifted from this 4,000-ton floating crane and then dropped onto this carrier to take it to the construction front. Now, just make a little explanation of how this was cast. So you can see from here on this diagram, the cartoon, that you have a 50-meter long deck, and there are 2 decks. They were transported on this low loader, and 2 bridges acted like 2 rails on which this transporter can move, with a multi-wheel transporter to distribute the load onto the deck. Step 1, the carrier comes to the launching trestle. It lifts up the precast unit of the carrier, and the carrier moves back. Then you take the launching trestle, moves forward to the next span, and it lowers the precast beam. This thing weighs something like almost 2,800 tons. And then you repeat. So this is the cartoon, this is the real picture. You can see this carrier and the deck, 50 meters, 2 rails, and then it will move side to side and then drop the cable. So the speed of this construction was that we could do 2 decks or side by side in 2 days. And you can imagine that that is very fast, provided you have done the foundations in advance. That another view of the viaduct and the launching gantry. But as we came closer to the navigation channel bridge, the height, so the approach span was 50 meters, but coming to the navigation channel, the spans were like 140 meters. The idea again was to use precasting. This vessel here is exactly the same vessel, Swannon, that was used on the Queensferry Crossing. So actually it was working on the Confederation Bridge in Canada before it came to the Queensferry. And Confederation Bridge was very narrow, so they could actually lift a whole cantilever with this crane and then drop it on top of the cantilever. So you had and then the same idea was used on the Incheon Bridge, where over the pier, you could have a long precast unit, then smaller units. So this could be lifted by a crane first, and then using lifting tackle to do the rest of the sectors. So you can see over here, the idea was the same. This shows the unit sitting on top of the pier, and you can get an idea of its size by, again, these 2 people. So this is something roughly about 20 20-meter deep, lifted up, put in position first, and then you have these lifting frames at the ends of the cantilever to pick up the segments from a barge on the water. And again, it shows completed deck. And then on this one, in order to speed up the construction and make the construction easier, the pile caps are actually above the water level, as you can see over here. So these were steel piles, casing, on which there were precast tubs that were put on it, and then the pile cap was cast into it. What this means is that the steel for these casings, because they will rust away in say 30 years or so, are sacrificial. And so the piles are designed so that the concrete inside the piles will do the long-term structural work. So the navigation bridge, similar techniques, that the whole of the backspan, 110 meter long, was prefabricated off-site. With a 3,000-ton floating crane, you can see from here, you will lift them up and put them into position. So you can start beginning to get the feel that when you're doing sea crossing bridges, reality is that's the main effort is actually mechanical engineering and not so much. In the end, it is a civil engineering project and the civil engineering product, but the construction is very mechanical plant. So heavy cranes, lifting machinery, and I think this is going to become more and more. It's going to be what kind of mechanical equipment one is going to use to speed up the construction, and what in quality. Quality would mean we prefabricate off-site in factory conditions and then lift the units into place. That's the completed bridge with again the dolphin protection to the backspan piers and then for the main tower. But, you can also design, we have done designs where we don't use dolphin and we simply design the foundation to be able to take the ship impact. I come down a little bit further south from Korea to Hong Kong, Zhuhai, Macau, and this is one of the jobs I really enjoyed doing. So I was doing this at the same time as doing the Queensferry Crossing in Scotland. And this just shows a picture. And at the moment, this is the longest sea crossing in the world. Now, why was it built? There always has to be an economic reason for any large bridge like this. So you can see from here, we got Hong Kong over here and Lantau. By the way, I live just around here on this island called Lantau. And that's the airport. And what was the reason for the bridge? There were actually political reasons as well as economic reasons. Political in the sense that there's a desire to unite or get closer between mainland and Hong Kong. And then Macau, which was also used to be a Portuguese territory. And it is a bit like Hong Kong where they have our own administration. So it's a three-way link up. Before this bridge was built, it would take something like 4 to 5 hours to drive up from Hong Kong, go across the Human Bridge, and then come down to Zhuhai. And showed the satellite photograph. Now, I was lucky enough personally to work both on the mainland side and on the Hong Kong side. So the Hong Kong side was done to Hong Kong standards. Again, we had to satisfy both codes. And you can see from here that there's a tunnel here, very similar situation to the Arup crossing. And the reason for that is that we got the airport over here. So this is a major navigation channel to Shenzhen with very big ships up to 300,000 deadweight or even 400,000 deadweight. And if had we put a suspension bridge, the towers would have been on the flight path. That's why a 6 kilometer immersed tunnel was done. I would say I'm not personally involved in that, but on the bridges. And then we have about 23 kilometers of bridge on the mainland side and about 12 kilometers of bridge on the Hong side. So boundary crossing facility, the boundary crossing facility is about 54 kilometers. Shallow water, not very deep around here, 6 to 7 meters, is deep around here, 20 kilometers, and it's exactly the same situation, minimize obstruction to the water flow. So the design philosophy was design life of 120 years, preservation of the navigation channels, flood control, environmental protection, aviation height restriction protection, protecting the existing installation, utility services, boundary crossing facilities, layout control. I just put that in, and that would be typical of any major sea crossing anywhere in the world. So once again, the pile caps were buried. The spans were made as long as possible within economic reasons, and try and keep the water flow through the bridge. The marine viaducts, and this was not done by me, the final development. This is actually the Chinese engineer. It's a very clever bit of engineering. You can see that these are buried pile caps. I'm not sure how this was built. And the problem was that the water level was up here, and how do you build this pile cap, which is down in the seabed? This shows the shortest, we call the shortest spans towards Zhuhai, and then the longer spans of 110 meters. These are one very wide box, something like 35 meter wide, carrying 3 lanes and a hard shoulder in each direction. And these were orthotropic box girders. Orthotropic means it's fully steel. So I showed you elsewhere, like a link on this would be the typical construction to reduce cost would be to have a pile cap at water level. But because we are trying not to obstruct the water flow, the pile caps were buried. And then how can we build this fast in some kind of a precast method? And this is where the Chinese engineers came up with some brilliant ideas. So what they did was they drew steel piles, and then they dropped what we call a precast concrete tub with some voids in here where the reinforcement would come out. But you can imagine if you drop this, all the water will come in. They came up with this clever idea of a grommet, of a seal. This seal was brought down with this because pile cap put over the steel pile and then inflated to create a water seal. This is first time anyone has tried to do this, and it's going to change a lot of construction in the world. So it means that when it's like a seal, and then they can pump out the water to work in the dry. But to do that, and you can see very similar idea to the Horizon Crossing, where this time they went one step further, where the pile cap and the column in some cases were cast together. And then what I really think was a brilliant idea was that on the pile cap, they had steel formwork around to drop it over the pile so that when it is dropped, it can be done in the dry. So again, I show you the size of that. And the whole contraption with the pile cap is dropped over the piles. You have the seal over here. This then becomes a cofferdam done offshore in the dry. When you drop it in the water, it becomes a cofferdam. And then when they do the seal, they can just remove the water and then all the work can be done inside the dry. So again, it is showing how mechanical way and mechanical plants and mechanical systems are the future of building civil engineering bridges. The decks, again, were cast, prefabricated offshore. And then you can see from here, trailed out, brought to the edge of the Pearl River Delta, and then floated out and lifted into position. And for the 110 meter, they had 2 floating cranes to be able to lift this. I'll talk about Zhizhou Bridge because this bridge has kind of become the symbol of Hong Kong, Zhuhai, Macau. And if you actually, or it used to be like 2.5 years ago, if you landed in Shanghai and then they had this immigration channel, they actually had a picture of this bridge. And I'm doing, just to let you know the idea, this was my original idea, hand sketch. And what I was thinking about was to do some kind of a nautical theme. So thinking of a sail, a boat, mast of a sailboat. I had the idea of making something like this, like a bony structure, and then doing a cable stayed bridge. And the main span was an orthotropic deck, and the back span is composite because you need a back span to be heavier than the main span in order to balance the bending moments. So on the left-hand side was what we presented to what was the joint committee of the from the client side, and but I still remember this when they went very quiet, and then I could sense that there was something not quite right. So I said to them very bluntly, is there something you don't like about this? And they said, and one of them said, look, you know, we Chinese don't like asymmetry. We like something to be symmetrical. So actually, I did say with a smile, I said, okay, no problem, we'll give you another tower. You will put 2. And everybody was smiling. They said, yes, that's what we want. So that's exactly what happened. And that was what was taken forward. So instead of a single tower, we had like 2 towers for symmetry. And that's a graphic of the bridge, pretty close to the original idea. And then again, you can see from here, the tower made in steel, off-site, prefabricated, and then lifted into position, as you can see from this floating crane. And that shows the bottom right-hand side, shows the construction. And that's the completed bridge. And this is looking from Zhuhai towards Hong Kong, and the background is Lantau Island. That's the airport. And as I was saying, I actually live on this island, on the other side of this island. And you can now drive. What used to be a 4-hour journey is about 45 minutes to come. And that's the bridge I was just talking to you about. So it gives you the feel and scale of the bridge. Then when I was doing this bridge, I was also doing the bridge in Scotland. And actually, this is probably one of the most interesting for me. It's quite interesting. Because this bridge is located, and I don't know if Baria has been there yet or not, but Baria, if you haven't, you should make a visit. And this is near Edinburgh. And you can see on this picture is the 1890s railway bridge across the Firth of Forth. And the 1960s suspension bridge, and that's the 1960s suspension bridge. But for me, it is something kind of special because when I first came to UK in January 64, then in about June, I think it was June or July, I hitchhiked with my brother around Scotland, and the bridge had not yet been opened. And we took a ferry from here. Queensferry was on. And I still remember thinking, I wish I was the designer of this bridge. So to be given a chance like 50 years later to design a bridge next to that was really something very personal and quite emotional. Now, interestingly, we were looking at this bridge in the 1990s. Now, had it been built in the 1990s, it would have been a suspension bridge, because in the 1990s, the longest cable stay bridge was about 450 meters span. And it was a bridge that had been built in Vancouver. But by the time it was not built, by the time it came to 2006, 2007, the state bridge technology had moved on. And as it happened, we were doing the 1,018 meter span Stonecutters Bridge in Hong Kong. So the consultant before us, it actually happened to be AECOM, were doing the feasibility study, and they came up with this pyramid towers. And the reason why there are 3 was that this tower could be sited on what was known as the Beamer Rock. It's fortunate we had this Beamer Rock, so it made sense to put a tower on it. You can see from this graphic that if you had a pyramid tower, you had a big footprint over here. And you may ask, why is that a pyramid tower for a 3-tower cable stayed bridge? The reason for that is that if you have a 2-tower cable stayed bridge and you put loading on it, the deck will deflect and it will try and pull the tower over. But because you have backstays and you have anchor piers, it resists, stops this tower from leaning over. You get small deflection. If you take exactly the same bridge and make 3 towers with the same size of the tower, you can see what is happening over here. When you load this, it doesn't have this kind of back anchor piers, and it will allow the deck on the other side to go up, and the tower leans over, and you get a lot of deflection in the tower. So it becomes kind of the amount of bending moment and all in this tower will get very high. So there are techniques of getting over the problem. One is to put intermediate anchor piers, or you can connect the top of the towers, or you can cross the cables from top of one tower to the junction of the tower and the deck, or you can cross the cables. Now, cross the cables was an idea of Professor Neil Skimsing, but he told me later it was actually an idea of one of his students in the early 90s, who actually investigated and found that if you cross the cables, you can stabilize the central tower. And what that means is that we then looked at a parametric study, seeing how many cables we had to cross in order to stabilize this central tower. And we found that if we compare that 3-tower bridge with a 2-tower bridge, with the same size of the towers, if we cross 6 pairs of towers, we could bring the deflection down in the center span to virtually the same as for a 2-tower cable stayed bridge. And then we found that the bending moment in the tower can be brought down quite a lot, not as much as for a 2-tower bridge, but still quite a lot. And that could mean that we could actually have the same size of tower for all the 3 towers. And you can see from here, we looked at an orthotropic deck and a composite deck. Orthotropic, again, as I was explaining, is all steel. Composite means that the lower part is in steel and the top is in concrete. So without crossing the stay cables, you get very high bending moments in the blue line. When you cross them, you can appreciably reduce the bending moments. And that was what was taken forward. And in terms of visualizing, it's like a frame. So you can see over here, we have 3-tower bridge. When you load this, you're actually creating this like a frame because you overlap. So you're getting decompression in these stay cables, and you're getting tension in these stay cables. And you can see that with the crossing of the stay cables, we can appreciably, not appreciably, but we can reduce the deflections. But that was in terms of looking at it from the side to see how it happened. The other thing, of course, was what kind of tower and what kind of deck we should use. So what I was trying to make sure that we do not, or let me put it another way, we want to have a visually good neighbor to the existing two bridges. What we did not want to do was to dominate the other two bridges by this third bridge. So we wanted them to be able to visually live with each other. So we looked at mono towers, we looked at diamond, like 8 towers, things like that. I think you can see from here that all these 3 towers, like diamond, A thing, they become massive and they start to visually dominate the other 2 bridges. Whereas we just have a single mono tower, it's more in keeping with the slim tower of the suspension bridge. That's what was taken forward. And this is a graphic done very early on. And you can see like 3 centuries of bridge technology here. Sort of 1890s railway bridge, 1960s suspension bridge, and we opened this bridge in 2017. And you can see how the sizes, even though this is a railway bridge, you can see how the sizes have reduced, and by the time we built in 2017, it's a much slimmer bridge. But the old suspension bridge suffered from having to be closed every now and then because of persistent high winds in Scotland. So there are wind barriers, wind shields, and this is a wind tunnel test to see whether this truck, so this minibus, will not fall over in high winds. What happens in very high winds is that tall-sided vehicles can fall over. So we have porosity through there, roughly 50%. But I've seen many bridges where they have done windshield and they are totally, you can't see through them. And so I wanted to avoid that. So we put these transparent louvers so that people could actually admire the view as they drive across. And that's the final design. Just to show you a little bit of construction. So there were pile foundations and caisson foundations. In the end, the contractor opted for caissons. And it shows the steel caisson being put in the bottom of the sea. It's about 20-meter depth of water. And the deck for the bridge was actually fabricated in Shanghai and brought to Scotland. It shows how now we are so integrated between different parts of the world. So this factory that built these decks also built the deck for the crossing in San Francisco Bay Bridge. And this factory usually makes ships, but they also now do fabrication for steel bridges. And they have their own vessel that can deliver. So it was a composite deck, and there was concrete on top and a box underneath. This was brought from Shanghai to Edinburgh, offloaded on the multi-wheel loader, taken into a factory where, in factory conditions, the concrete slab was cast. Once again, ensuring that we get quality construction. And then that is the completed box taken out of the shed. And then just to show you some photographs of the construction around the tower. This is the temporary formwork. And then if I had time, I will show you some erection, but this is the completed bridge. And you can see again, this is a real photograph of the 3, again, the 1890s bridge, 1960s bridge, and 2017 bridge. So this area has now been given the UNESCO World Heritage Site status because of these 3 bridges. I jump back to Asia, and another very interesting job. I think you will all know where Brunei is. And like a lot of the colonial history, when the British took over Brunei and Malaysia, they conveniently cut Brunei in two. I say that a bit cynically, but this is what they did because they wanted to have access through here into Brunei Bay. The chap whose name was Roger Brooke, who became the Raja of Sarawak, of all places. And Brunei was a very big sultanate. It had the whole of the west side of Brunei and parts of Indonesia. But after the British came, they were actually reduced to just two small bits of land divided by Malaysia in the middle. This has caused them a bit of a problem because what it meant was that you have two boundaries between, so if you want to, or if you wanted to drive from Brunei from one side to the other, you had to go through two checkpoints. And that was a hazard. It meant that it took something like 3 to 4 hours to go from center of Bandar Seri Begawan to Bangar in Temburong. And if you the sea route was just, it used to be known as the flying coffins, a lot of accidents, a lot of deaths. And it was like a waterborne thing, and that would take something like 1 to 2 hours. And you can see, again, there was no bridge. There were some small rivers, but they had to have ferries. So the government was keen that to unite both sides. And we were lucky enough to be invited to design it for them. So the whole project is like a mini Hong Kong Zhuhai Macau Bridge, something like 30 kilometers in length, 3.6 kilometers on land with 3 tunnels, and then about 14 kilometers of viaduct across the estuary, and about 12 kilometers across a mangrove stone forest. Mangrove stone forest is actually water is just at the surface and very, very soft. And these are some mangroves and typical swamp trees. There were 2 navigation channel bridges, the marine viaducts, and these were all computer graphics that you can see. And this is going through the rainforest. This shows diagrammatically, again, in more clarity, the tunnels, the marine viaduct, and then the swamp viaduct, something like 30 kilometers. Very shallow water. I mean, you can see me standing in there in this very shallow water. Very soft soils. If you can, there were like 15 to 20 meters of very soft soil into firm clay and then into sand. And how do you build across here? So the design was based in a way on what we had done in Penang in Malaysia. We used what we call spun piles and tubular piles that you can drive, have pile caps above the water level, short columns, and full precast decks, a bit like the Incheon Bridge. And we use high damping rubber bearings because there's a bit of seismicity in Brunei, sorry, in Borneo. And then modules of 6 by 50 meter spans. The problem then was, how can you access this very shallow mud flat? So we had to do dredging along the route. Again, ideas borrowed from the Penang Bridge. On this island, we created a disposal area for the shallow mud and sand, and then these were pumped into the shallow area to allow access for the piling barge and allow access for delivery of piles and delivery of concrete. This shows the factory. The contractor for this was Dalam from Korea, who had actually also worked on the Incheon Bridge. So we kind of borrowed the ideas from Incheon Bridge. And again, full span launching. This shows the inner mold of the decks. And these 50-meter span decks were stored and then taken to the site on this barge and taken to the site. Now, launching, as you saw before, and I showed you before, when I showed you the Shenzhen Bridge, where it was one side being erected first and the second side. You saw in Incheon the straddle carrier, which is doing one deck first and then the other deck. But this was not our idea. This was the idea from the contractor, though the design was ours. They worked with Cleveland from UK, and this is the first time in the world they came up with a launching gantry that can lift two decks at the same time. So they were lifted up and then slid inwards, which meant that you could erect two decks in a single day. And that really speeded up the construction. So what it meant though, even though it was 14 kilometers long, all the foundation and piers were being done and the erection of the deck was very, very quick. I'll talk about then about the navigation channel bridge. Somebody needs to mute. Okay. So there were two navigation channel bridges. There's one navigation channel to Limbang in Malaysia, and then this comes into Brunei. Not very big span, I mean modest spans of something like 260 meters. So one bridge has got a single tower and another bridge has got a two tower. And because it was Brunei and my client or our client said, Naeem, we want you to design something that would have Islamic features and can represent, because Brunei being an Islamic country, they wanted something. And I said, yeah, sure, let's. And my immediate idea was to think of Islamic arches. So the tower design, what was the genesis of it? So, as I said before, Malaysia had cut Brunei. So Brunei has 4 districts: Vilayat, Chutong, and then the central area, Mora, and then Tenggerong. How do we unite them? Now, you're all in from Maldives, so this is not new for you. That in the Islamic architecture, we have a lot of arches, different kind of arches that you can see from here. You can see this again, the masjid. And in Granada, in Spain, there's some very nice architecture, Islamic architecture. If you know, in Islamic architecture, we have decorative screens that actually also allow the air to come in. So I was thinking of this, and of course, this is very elaborate in a masjid or in a mosque. You can't quite do that in a bridge. But you can see that we tried to make an arch, and these are the 4 architraves. Architraves are 4 planes, one behind the other. So our idea was to have 4 architraves to represent the 4 districts of Brunei, and then have a single window to represent the unity of the 4 districts. And then we put a tower. And we had Allahu Akbar, Subhanallah, words on the face of the tower. And also Alhamdulillah. So that's an architectural term, but in engineering term, it was actually a diamond tower. So you have 2 legs, and then the legs come in. So structurally, it's actually a diamond tower. And you can see from here that the cross section is hollow legs, and then when they come up, we have this infill. Now, in many cable stayed bridge, you will see 2 arms coming up, and then the 2 arms meet at the top to become the diamond tower. But here we did the infill wall, and this also helped us because we have a staircase that goes inside, and you can actually go right to the top for inspection. So you have a single tower bridge and a twin tower bridge. And this shows some construction. This is towards Mora district. You can see from here going away into the distance. The other cable stayed bridge is here, and then into the Somme forest. And some completion of this is like 260 meter span, about 20, I think it's about 24 meter clearance, and then the low level viaduct. And that shows some views of the Brunei Marine Viaduct. And this is a shot of the early morning as the sun is coming out on the east. Then I'll jump to hopefully the final one on this, which we are working on now at the moment. Very similar things to what I've been showing you before. So at the mouth of Manila Bay, you have a thing called the Corregidor Island. And you have the Bataan from the one side, and you have the CBD of Manila. And if people have gone to Manila, you will know that it is one of the worst traffic situation at the moment. But they are trying to address it. They are building MTRs. They are building new roads. So from here to driving down to there, again, very similar stories to what I've been showing you before, would take something like 6 hours. And the idea of this bridge was to cut the journey down to about 45 minutes, or center to center, maybe 1.5 hours. So the bridge is around here, and that's you can see Philippines. So I thought I might just show you some navigation issues, which are also done for the other bridges. So you have this famous Corregidor Island. It's a national monument, the island itself. For those who want to know history, the Japanese invaded, and this was known as the Death March, where they walked the prisoners, and many of the prisoners died on the way. So they have a very emotional tie to this area and then to this bridge. So there were 2 navigation channels. One was 2.2 kilometer wide. The other is 3.2 kilometer wide, and then some massive marine cables. Just to give you a feel when you're doing these things, so these are the traces of the navigation. This is ADT, automatic detection systems. You can get this data, you can analyze, and you can get an idea of the size of the bridges. I'm just trying to do this as an example of what is behind when you're doing, how do you determine the size of the bridge? So 2 things. One, you have to make sure that you have a sufficient width for ships to cross each other if they're going across each other. You need to look at oops, somebody's can we turn those videos off? On my screen has come up the sort of videos of a few people. Okay, thank you. So we look at the current shipping patterns, possible future trends, the mid-ocean conditions. From there, you can assess what needs to be the width of the channel for the required spans for vessels to safely pass under the bridge. And then the air draft assessment. The air draft for a ship, and they're getting bigger and bigger. Vessels are getting massive now. The new generation of container vessels are going to be extremely large. And then they might actually not be able to enter some of the old ports because there are bridges across them. So it's a kind of future-proofing the entrance to the Manila docks to make sure that we can take very large ships. So you're looking at the sea level, including the sea level rise due to climate change. Look at the air draft of the design vessel, the air draft buffer zone. You need a bit of a buffer zone for wave action, and then allowance for the bridge will deflect. And sometimes many bridges will have an inspection gantry underneath. So we need to allow for that, for the bridge gantry. There are certain, and then you can work out what should be the air draft safety zone, and then decide on the height clearance that we need. So I just showed this to you as an example. And then we do ship simulations. We did ship simulation for Stonecutters Bridge. We also did for Queensferry. This is again a typical ship simulation for the Bhutan-Kabita Bridge done in Bhutan. They have one of the best simulators in the world. You can actually go inside the simulator. It will actually give you the simulation of a vessel in sort of real time. And we have real pilots. These are real views, and this is a graphical representation of the bridge, but it looks very real. And the pilot is trying to take the ship safely. And we do simulations of engine failure, simulations of fog, trying to make sure that he or she can safely take the ship underneath the bridge. And actually we had to slightly make it longer. They were not comfortable with 800 meters, so eventually we went to 900 meter span. So these are the sort of studies one does to do that. It shows the final outcome. Many alignments were checked. This is the final alignment, 32 kilometers all the way. A 400 meter navigation channel bridge on the north side, and a 900 meter and navigation channel bridge on the south side. Give you the scale, and as we hit the Bhutan side, we start to climb at 3% towards the road. And you can see on this graphic below, these are all the ships. And a lot of ships are anchored, and there are smaller ships. And we're trying to thread our way, because we also are looking at, in a storm or in a typhoon, if the ship loses its anchor, starts to drift. We study the drift of the ships, and then we're trying to find out what would be the impact load. This gives the representation of the bridge, starting from Bhutan coming towards Cavite. So what we did was we said, okay, we're not going to do two major bridges for the same heights. We are saying we will restrict shipping to a smaller size on the North Channel and get the biggest ships in the South Channel. That's why this is higher and has a longer span. So the North Channel is shorter span, South Channel is a longer span. And this shows an overview looking from the Manila side towards Bhutan with the two navigation channels and a future connection to Corregidor Island. So it's a 2-lane and a hard shoulder carriageway. It shows different kinds. So even though you're saying 32 kilometers, it consists of land viaducts and marine viaducts, approach bridges to the navigation channel bridges, and then the navigation channel bridges themselves. A little bit on the marine, and at the moment we are developing it. And just to go back in the earlier part of the presentation, we were showing you classical ways of balanced cantilever, span by span, or like was done on the second Penang, what we're doing in Brunei, excuse me, and then Incheon Bridge. So we are doing something very similar, of pile foundations, precast pile caps, precast piers, caisson, and then looking at what was done for the Confederation Bridge, because we need to again have speed and quality construction by prefabricating offshore. So these are photographs from Hong Kong, Zhuhai, Macau, and we will do something very similar for Bhutan, Cavite. Ideas borrowed from the Hong Kong, Zhuhai, Macau bridge, same kind of ideas for this bridge. And then the navigation channel bridges. For interest, Philippines and this bridge is one of the bridges in the world which has got all the extreme conditions that we have to deal with. So it has one of the highest seismicity in the world, one of the highest typhoon winds in the world, the deep water, which is 50 meter, and then some of the biggest ships. So these days, we can actually design for these extreme environmental conditions and extreme physical conditions of ship impact, if we are able to design them. And how do we do for seismicity? Not an original idea. It has been done, was done in Greece. It's currently being done for the Stonecutters Bridge in Turkey, where you have to do base isolation. What that means is this is like a fuse. This is soft soil coming into rock. So we drive some inclusion piles. They are like tubes to transfer the load to a deeper level. We have a stone mat. So when an earthquake comes, this tower can actually slide on the stone mat. So it acts like a fuse, similar to the high density damping rubber bands I showed you on the Brunei Bridge. So, but for wind, we would have to separate the decks like we did for Stonecutters, because separating decks means they are more aerodynamically stable and it will not flip over. You may have seen the Tacoma Narrows Bridge Classic Bridge disaster in the 1930s when they were not aware of the aerodynamic stability of bridges at that time. And everyone has learned from that. So these techniques have been used, towers similar to what we have done for Stonecutters. This idea here, inclusion piles, were actually done for the bridge in Greece for the first time. So we're going to do similar kind of ideas, huge precast caissons up to, this height will be something like 60 meters. We do the inclusion piles first, float these out and drop it down over pre-formed plug piles, and once we have the thing in place, we will drive the piles through there. Do a second solution would be to put piles all the way down to rock level. So this gives you an idea of this is what we are actually developing right now. So what are the conclusions? I mean, what is actually happening is that nowadays long span and long sea crossing can be built in extreme environmental conditions, as I was saying before, such as deep water, ship impact, high winds, and high seismicity. But for fast and economic construction, we will have to do large offshore prefabricated foundations and also the deck units, which will be erected by very large floating equipment as necessary. So it's very mechanical plants are being developed. We are already beginning to see, and we will see more and more, that we're going to have robots to do the construction. Many parts of even now in Hong Kong and actually in other parts of the world, robots are being developed that can do, which means that the safety should get better, because unfortunately for almost every bridge, we lose lives, which we need to avoid. We will see more composite. When I say composite materials, like in aircraft, we can do parts of the bridge to make them lighter, replaceable parts, because we need to start thinking about much longer design lives. So like a car, if part of a car goes wrong, we can replace the parts. And I think people are beginning to think that we should be able to have replaceable parts in the bridge. Obviously, it's not possible to change the foundation because that's extremely difficult. But even now we have moved forward, because on a cable stay bridge, we intend, when we say 120-year design life, the reality is that after 60 years, all the stay cables will be replaced. You can't do that on a suspension bridge, but one can look ahead where you could have double suspension cables. The facility for that is done from day one, and we can do that. We are already seeing drones already being used for inspection and rehabilitation works. Not quite rehabilitation, but definitely for inspection. And I think this is going to become very common in the future. I just put this in to say that we can have all of these things, but this is a message I always took to my designers who think that there will be no work for us. But the reality is there will always be a need for it. Because someone somewhere has to come up with the ideas. One of my friends said, design does not come from heaven. Someone, somewhere, some guy has to come up with a design. And that needs to consider the environmental and cultural aspects. To me, the client's budget is paramount. There's no point in doing a Rolls Royce of a bridge when a Toyota is good enough. And that a lot of my fellow designers, I believe, have a hedonistic approach. They want to do something for themselves. They want to create the longest bridge, the biggest bridge, a huge kind of architectural statement, but maybe the client cannot afford that. So any design that we do, I now, after years of doing this kind of work, I say, I want to know what the client's budget is, and we design whatever is the most suitable within the client's budget. Of course, you need to then consider the aesthetics, the appropriate construction techniques, and do a bridge that will, what I will say is combine form and function for that particular site. Thank you very much. I can take any question now if you want. Okay, thank you.
Anybody who has a question, some clarification, comment, please raise your hand and I will give you the mic. I think Naeem has done a very interesting presentation, and he's also given us a lot of time. So let's say we will allocate 15 minutes for this. Ismail first. Ismail.
Yeah, thank you, Naeem, for an extremely inspiring talk. I wish I were younger so that I could actually opportunities in this. And I just wanted to know about you. You mentioned about the Swan being moving essentially across the Atlantic to Canada and then back again to Europe. I was wondering, at what stage do you start considering the kind of the available plant for your concepts, or do you kind of start on day one to look at, okay, maybe this is what works? So I just wanted to know how you factor that in. At what stage of your design or your conceptual development of the project do you start thinking about that?
Okay, so that is a very good question, right? So when we do a design of the bridge, it is not just about the final product. For a bridge, right from day one, we need to think about what construction method we're going to use. Because nowadays, the construction method is what is going to drive what kind of bridge. And the reason for that, again, is we are saying, to repeat, that speed and quality. Speed in the sense that we do things in parallel. So while we're doing the foundation, we're also doing the deck. And then we are thinking, okay, for this bridge, what kind of bridge and what kind of equipment we should use. So right from day one, we actually plan, because we don't leave it, if it's an engineer's, or what I say, the employer's design. And even for a D&B, where the designer does the preliminary work. So the construction method actually can drive what the bridge will be. So you can see on these large bridges, we are thinking about floating cranes, floating batching plants, floating piling equipment. You're doing that from day one. And the other thing is that the bridge has very low redundancy compared to a building. Now, if you take a building, you have multiple columns. And if one column fails, you can still design so that you don't get a catastrophic failure of the building. But in a bridge, it's very little redundancy. So if you have a failure, you could have a catastrophic failure. So the design and the design stage is also looking at the construction stage. So we always say, we want to see how you're going to, if it's our desire, we give a schematic construction method, which then the contractor will say, okay, you develop it more. And then we will look at the method statements, make sure it is safe. So it is going to become more and more mechanical. And coming back to the Swan, we knew that this vessel was available. So when we did the design competition, we actually literally from day one did our design based on the availability of this. And we knew this crane was coming free from the Confederation Bridge. So actually from day one at the design competition, even before the contractor actually hired the vessel, we had built our design based on that vessel. Okay.
Thank you, Naeem.
I hope I'm not gobsmacked anyone. I mean, please don't feel shy to ask questions. You know. Okay, I mean, if there are no questions, I'll maybe just give it a minute. There's also apart from the design, there's also the issue of procurement, right? So there are various techniques of procurement. You can either have an employer's design, or you can have design and build, or you design and build to what I would call a specimen design. And both for Oresund and even for this particular bridge, it may go down. Oresund definitely went down the design and build bridge. Queensferry, where we did, was the same. So the procurement method was that the employer's designer does the preliminary work, does a design to a high degree of development so that he has solved most of the problems, make sure that the alignment is right, the general arrangement right. We then go to design and build. So the contractor is starting from a known quantity. And this is kind of my mantra at the moment. I'm saying to many employers, this is the way to go, where you do the preliminary design, feasibility design, then you go to tender and you then get the ingenuity of the contractor to see how he can build it. And in that process, if we are lucky, we should get best of both worlds. We should get an economic design. I mean, the contractor is not worried about what kind of bridge and all. He's already got a bridge idea that he can develop. And Oresund has been very successful. Queensferry has been very successful. And I may imagine that even Batan Kavita may go that way. So apart from, I'm saying, Ismail, apart from design as such, you need to decide very early on also what is the procurement method that an employer may want to use, so that you build that into your time scale right from the beginning for the very, very large crossing.
Naeem, if I may, can I just ask a question?
Sure.
A very interesting and mind-boggling the design for sliding tower foundation, the entire foundation to slide.
Yeah.
I was wondering what actually happens to the deck on top. I was actually lucky enough to be an observer and a little bit of a hands-on observer in the Akashikaikyo Bridge in Japan.
All right. Yeah.
Yeah, and I think just after they finished the actual towers, they had the Kobe earthquake, and they actually moved relative to one another during the earthquake, and they. I remember they was telling us that they actually had to relay the suspension cables and everything because of the change in because the towers had moved. And I was wondering how do you actually design for the foundations of the tower to move? What happens to the deck?
Okay, I mean they were lucky on the Kaishika Cave because the tower was on land, and fortunately for them, the earthquake happened before they even erected the cables. So if you remember, that the tower moved by almost the distance between the towers increased by about 1 meter. But they were lucky that the towers had not yet been built. Now, this kind of bridge, which is, as I said, I can't remember the name of the bridge in Greece that were first used this. This is actually in the sea, so it's not actually on land. And because it's in the sea, but you can also do it on the land actually, I come to think about it, that you can have this mat and thing where in a seismic event, you allow the thing to move. Now, it's so that kind becomes a fuse. In fact, they're also doing it for buildings. So in Japan and also in Turkey, and even for factories, the building structure is actually on sliding bearings underneath, damping bearings. So when the earth moves, you've got enough weight in there, and it can move underneath. And because you have the whole deck, it will actually, there might be a slight movement in the end, but you have actually made sure that you are not damaging, and you can actually work it out that the effect on the deck is can be managed. You may, the movement joints on either side of the deck, however, could be completely smashed. Because if we have a longitudinal movement, we say that in an extreme event, we will let the movement joint fail, and then we can come and replace it, and we can do that. And on Chinakale and other bridges, even though we have a sliding at the tower level, we also have dampers between the deck and the tower, and those dampers can actually hold the bridge. So you allow the thing, and you're damping out the seismic forces. Now, I've done a bridge in California for the Long Beach. If you ever go to Long Beach, you'll see there's a bridge there called the bridge in Long Beach. We have dampers at deck level, we have dampers at the tower level. And so for seismic technology, you're actually using like a shock absorber in a car, basically. And you can actually take those forces.
Thank you. I suppose that leads on to what you were saying before of replaceable parts, maybe replaceable joints, and yeah. But yeah,
again, just to finish that point. So on the Port of Long Beach Bridge, the dampers will have to be replaced after a major seismic event. Yeah.
May I ask a question?
Sure.
Thank you, Naeem. It was a very interesting presentation. My question is more related to maintenance part. So if we have, for example, a steel deck, somewhere down the line, we would need to sort of maintain, repaint, or do the protection. So how do we deal with that when it is overseas? Yeah.
Yeah, I mean, I could spend hours talking to you about that, but I'll try and give so what is unlike what was even done, let's say 50, 60 years ago. The modern bridges, and the best example I can give you is our Stonecutters Bridge in Hong Kong. So right from the beginning, we have designed in access to all parts of the bridge. And we make sure that every part, and in Scotland, every part of the bridge has to be within touching distance. So what that means is that we have gantries below the deck that can run underneath the deck. We have on the tower, we have like a building management unit crane, like we do on buildings to clean the windows, a BMU. We have a vehicle that can actually now travel up the deck to look, and you can look at any part. But actually what is going to happen that a lot of these kind of mechanical systems of inspection are already being replaced by drones. So what we have done in Stonecutters, where we have accesses, also the mechanical accesses to get down, because we can do that. And we make sure that when we do in future the maintenance, we have a way of getting to the surface to do the maintenance. So underneath the deck, we have these movable gantries where we can repaint the whole of the deck of the underside. We can inspect. Inside the bridge, we even have a small two-man train that can run along inside the deck, where they can easily get to an incident. So we have inspection for the cables, inspection for the decks. We have hatches where we open up and get inside. And then we've got dehumidification inside the steel box to make sure it does not rust. So unlike what happened before, nowadays we're designing it very differently. It's like a building where we want to take every part. And then what is happening is, and I think Maria is UK, she knows, we have a BIM model. We have full details. We have what we call the asset management system, where we have a big database of all parts of the bridge, even to the extent that when the guy goes on the field with his little iPad and he sees something wrong, certainly he can press a button, and by the Wi-Fi system, he can actually look at all the drawing and details. And we have coming up with forms automatic where he can record what is happening, and they can see what is happening to the bridge, the structural health monitoring systems and all, and you can record very systematically now as the bridge life goes on, what is going wrong, and so that you're not waiting for things to collapse or really go wrong. You have a managed inspection systems, you're looking, and then you can intervene in time. So just like a human body, if you have temperature, you know there is something wrong, but you might not know exactly what is wrong with you. But at least the temperature is telling you there's something wrong. You go and see a doctor, and then he will examine you and do it. Or even a car these days with this gizmos inside can tell you what's going on with the car. We are also trying, we haven't fully succeeded, I will have to admit, but that's where the technology is going. Not all systems are perfect at the moment, but the idea is to do a structural health monitoring so that, for example, in a steel bridge where we are going to have well failures, we have extensometers, we have instrumentation in there that is telling us. But it's not that easy. And I have to be quite honest with you, because you've got masses of data. How do you manage that data? But that is the challenge, but that's how things are going. So for example, in a car now, when you go for servicing, the guy puts in a little thing and he's telling you what is wrong in the car, or it is trying to tell you. I'm not always fully convinced, but it's trying to tell you. So we are heading towards that, and I think technology will get better and better in that thing. And nowadays, in the old bridges, we had structural health system with the wiring all over the place that used to go wrong. We're now going wireless. A lot of data transfer, like on a 5G system, it will tell you what is going on, and ping, it will give you a message where you have the inspection people and they can examine and say, okay, what they're really doing is there's a change of behavior in the bridge, then you know something is going wrong. If it's not behaving as it should be behaving. So that's the way the technology is going, and it'll get better and better.
Thank you. I think my concern mainly was that in other countries, for example, if we consider UK, we have these set systems where there will be like periodic monitoring, and then they will do the periodic assessments and things. But
Yeah.
when we introduce megastructures to new countries, these systems are not set up in place. So
You
I
know,
think
that is
concern,
exactly, yeah,
yeah.
that's exactly what we have. I don't know whether we have fully succeeded, but on the Brunei Bridge, we have done a massive O&M manual. We have
Yeah.
done the whole inspection regime. We have tried to get them to set up a bridge management unit, and we hope that they will do it. Now, whether they do it is something else. Now, there has to be a will to do it, but you have to do that right from day one. Not so when we build up the bridge, we are actually literally giving an O&M manual, inspection techniques, the criticality ratings and all that business, and we say this is the thing and you must develop it. And so two things for that: you have to have good access. They need to know from day one what they're looking for, and we're also trying to say, where do you think things will go wrong? And so many a country, it used to be, even in UK for the matter, they weren't that far. America was even worse. They never maintained and they never inspected. But if you want to get the longevity of your asset, you have to have an asset management system in place. Absolutely agree with you.
Thank you. That's all.
I think, Naeem, you have given us a lot of time, and that is a lot of content as well. On behalf of everybody, let me thank you very much for this presentation. I think it's something that we will keep on referring back to for a while, and would like to thank you and close this session really because
Yeah, thanks a lot. Yeah.
yeah.
Yes.
Isma, any closing remarks?
Yeah, I really echo your comments, Nave. I think this has been a very, very inspiring. And I think, Naeem, if you get some more Maldivian engineers going into the bridge profession, I think you are probably, you are the one responsible for it.
Yeah, we can do with more. You know, I mean, Baria has set the trend, so we're sure we can get more Maldivian engineers. We look
Thank you
forward
very
to it.
much, Naeem, and I hope we will be able to. I know you're going to be involved with the Maldives for the next few years at least, on the Male Bridge, and we hope you'll get some other time to meet up, and hopefully this time for a physical session, so that our especially our junior engineers can get to interact with you on a one-to-one level as well. Thank you very much.
All right. Thanks a lot. Thank you very much for attending. And take care. And Khuda Hafiz.
Good night. Good night.
Thank you, everybody. I think it's a good night and a wrap.
Yeah,
So good night.
Night. Good night.